In our second lecture, we will discuss about the function group examples. Like here, if we look, we will find that function group like amine basic group like that R contain N R double R, or it's NH2, it's amine, but this is here is a tertiary amine like Zystril, Zystromax, Vasotic, Baxil. Quaternary amine as a salt because it is ionized. It looks like ipratropium bromide, cibacol, fumaride, azo function group like this, which is that Rn double bond in R dash, which is about that like clozal, prontozil. Carboxylic acid group, which is acidic group like tequin, vasotic, ibuprofen, zestrol. Ester RCOO R dash, which is like that Ritalin, Tricor, Vix, Zaltane, Adalate, amide, which is that RCONH2 or NHR dash, like Sonata, acetaminophen, glucotrol, indomethacin, imide, which is that RCONHCOR dash, which is that look like two amide condensed with each other, which is imide. And it is like that macrobid, Avandia, phenytoin, Viagra, alcohol, which is that ROH, like Metrogel, Allegra, pseudoephedrine, Liscol. About that ether, ROR dash, which is that a derivative of water, H2O, HOH, okay? But here it will be ROR dash. Here it is like that Prelosic, Cerzone, Flumax, Tobrol, Zbitam, and Skilaxine. Phenol, which is that acidic, which is that AROH, which is a benzene attached with OH. If it is two OH in ortho position, it will be caticle. Okay, but this is phenol acidic group like ditryl, amoxyl, acetaminophen, azacol. Aldehyde, which are CHO, RCO carbonyl group, was attached with H. That's aldehyde function group like xenical. Ketone, which are COR dash, like that Renacort, Percodan, Tricor, Warfarin. Cyano, which is like that contain in Sonata, cimetidine, melerinone, sulfonic acid, which is that RSO3H, which is like that Cardura and Norvasc. Sulfonamides. Sulfonamides here is acidic if R2 and or R3 is H, which is that if it is secondary amine or tertiary or primary amine, it will be more acidic, but tertiary amine will be more basic. Which is sulfonamides, as you see, it will be like Celebrex, Viagra, Zistro, Retic, Amaryl, Zaroxylone, Flomax. Sulfoxide, which is like that Acifex, Prelosic, Sulfone, which is that like Vix. Sulfone is like that SO2 and R2. Thioether, which is RSR. It looks like ether, but it instead of O, it will be S, like that Zebrexa, Axid, Ceftin. Nitro, which is RNO2, like Adalate, Macrobid, Axid, Metrogel, and Clonazepam. Carbamate, which is that RNHCOOR, which is look like carboxylic attached with nitrogen or amine with that carboxylic group and R dash, which is that we call it as a carbamate. And this is like claritine, skilaxine, septin. Also, when we talk about the urea structure, in case of urea structure, urea is look like this area. That's CONN, that's urea derivative, like amidon, which is sulfonylurea, cerazone, glucotrol, all of these like that urea derivative. And about the phosphonic acid, which is that the phosphonic acid, as you see, like this, it's like phosphonic acid or the bisphosphonate, like Busamax, the alendronate, etodronate, and so on, this family. Okay, so that's about examples for function groups. But what about the rule of function group or the pharmacophores? Let's say that for a given drug molecule, function groups play a significant role in the overall water lipid solubility. The function group can determine about the water lipid solubility of a compound, route of administration, if it is more water soluble or lipid soluble, so this is affecting the route of administration, ability to interact with specific biological targets, which means that sometimes the drug can bind to the receptor due to presence of a functional group that can make a hydrogen bond with the receptor in the binding, receptor pockets in the binding, and some others not have the ability to make the hydrogen bond, so it will not bind to the receptor. So the ability to interact with the specific biological targets, mechanism of action, route of metabolism and elimination. It will be metabolized through the phase 1, then phase 2, or only the phase 2, or only the phase 1, or it will go through oxidation, reduction, which metabolism route it will go through, that is according to the function group. Duration of action, sometimes we make some modification on the function group to increase the duration of action or decrease the duration of action. Suitability for a specific therapeutic situation, tendency to cause adverse effect or drug interactions. We will discuss this in details now. Firstly, the role of the function group or the pharmacophores in receptor binding of drugs. I give example for enalaprolate. If we look at this example about enalaprolate, okay, so we will look here, guys, we will find that we have function group A, which is the carboxylic group, function group B, which is another carboxylic group, and the function group C, which is this benzene or aralkyl ring. Okay, so the function group A, what is the importance of it in binding to receptor? Enalaprolate, as we know, it is ACE inhibitor, which means that it should bind to the ACE enzyme, which is angiotensin converting enzyme, to inhibit it. Okay, and it's help in that treatment of hypertension and make some action as important action in the decreasing preload and afterload in people with congestive heart failure. Okay, let's back. So the function group A, which is that carboxylic acid, that provide initial ionic bond that allow this drug to interact with its target enzyme. And here, guys, what happened? This CO and this OH, it will leave, the proton leave, and leaves this with a negative charge. This negative charge will be interact with a positive charge in the bucket of the receptor, of the ACE receptor. So here it will make the ionic interaction between this function group of acidic function group, the carboxylic function group, with the binding to the target enzyme. And if we look, guys, about that, the function group B, which is that another carboxylic acid group, this carboxylic acid group, which is important to interact with the zinc atom, involved in normal substrate catalysis. Here, there is a zinc, okay, that will interact with the function group B, the zinc in the receptor, the target receptor. So this will help to binding to the receptor. And the function group 3C, which is that interact with a hydrophobic site and greatly enhance binding, which means that in this area, the bucket of the receptor will interact with a hydrophobic interaction. So in the enalaprillate, presence of the function group A help in the ionic interaction with the target receptor. Presence of the function group B help in the interaction with the zinc part of the target receptor. And presence of the function group C is important to make the hydrophobic interaction with the target receptor. So this can let the drug binding to the receptor of ACE and then give its action, which is that decrease the intrinsic activity, which is that inhibit the drug, the enzyme action. Okay, so another example will be a other example is a famotidine, which is a pepsid. We can find that the pepsid or famotidine is composed of the amidine, which is that in a box in the structure, this structure in the box, this function group called amidine, and the heterocyclic ring and the guanidine. Okay, we can find that the amidine function group that shown in this box is participating a key ion dipole interaction with an ionized carboxyl acid group found in the H2 receptor binding region, because the famotidine is H2 blocker, so it begins to binding with the H2 receptor and inhibit its action, okay, which is used for anti-ulcers, used for GERD, used for antacid, and so on. Okay, someone say how it look. Look with me, guys. As you see in the figure now, that this is the H2 receptor, okay, and this H2 receptor contains the carboxylic acid group, which is COOH, and this H is released and get the ion, which is that O minus or that O with one electron. This ion will begin to make interaction with the dipole part of the amidine, okay? And this is the ion dipole interaction. Ion dipole interaction. Someone say, Doctor, firstly, what is the meaning of that dipole or dipole? Dipole, which is that when there is, for example, SO2, look with me, it is S, I will explain here, SO, O, and here was it NH2, okay? If we know, guys, about that, this is a covalent bond between the S and N. There's two types of covalent bonds. The polar covalent bond and the non-polar covalent bond. Polar covalent bond, which can make the dipole action. The dipole, which means that partialized, okay, partial charge. Look with me. If we say here, guys, in this figure, that the covalent bond is composed of a sharing of electrons. This is electron from S and this electron from N. Okay, when there is a difference in the electronegativity between the nitrogen and the sulfur, as you see, that the electronegativity of the nitrogen is about 3, which is higher than the sulfur, which is at 2.5. So the high electronegativity is the nitrogen. Will try to attract the electron of the bond towards it. So this will make what? This will make this nitrogen has a partial negative charge, and the sulfur have about a partial positive charge. Due to what? Due to the attraction of electron of the bond from the sulfur side to the nitrogen side. This is will make the nitrogen crowded with the electrons, and it's give partial negative, but that the sulfur is that partial positive. Okay, so this is will make the dipole, which we call it dipole bond. Okay, and the dipole is a charge which is partial negative on the nitrogen and partial positive in the sulfur here. And this is will make the ion of the receptor attracted to the partial positive because it is negative ion, so it will attract to the partial positive of the sulfur here, and this will make the ion dipole interaction. Someone say, doctor, why it's not protonated here in that this structure? As we said, this part is amidine. Okay, and this part is amidine, and there's other parts like that. This is a heterocyclic ring, and it's guanidine. That's guanidine. Okay, so guanidine, amidine, and heterocyclic aromatic ring all are basic in their character. Okay, and the range of the phenotidine in its pKa is always about 6.7 to about 6.9. Okay, so in a pH, which is that the physiological pH, we know the physiological pH, the blood pH is about 7.4. 7.4. So at the pH of the physiological pH, okay, we will find that the pH is higher than the pKa. The pH is higher than the pKa. Okay, and that is will make the basic function group, which is that unionized in the unionized form in the pH environment of physiological pH. Okay. Okay. So for the rule of function group or the pharmacophore in increasing drug potency, this is number 2. So what we can say, we can look at this structure in front of us, that it is a statin structure, which is that different between lovastatin and simvastatin. If we look, we will find that simvastatin have a methyl group in this R, but lovastatin, it is hydrogen, not alkyl group in the R. Okay, so the methyl group here in simvastatin make the activity of the drug is more active than in absence of the methyl in case of lovastatin. So simvastatin has higher potency, higher activity than the lovastatin due to the presence of methyl group in this structure. So presence of additional function group can increase the drug potency. Also, when we look at the morphine which contain here in the R methyl group, okay, in the metabolism, it can be metabolized by N-dealkylation, which is a type of oxidation reaction. N-dealkylation, which means that that R or the methyl will become hydrogen. At this moment, we call it as N-dis-methyl metabolite. The N-dis-methyl metabolite is less potent than morphine by about 4 folds, which means that the morphine is higher potency by 4 folds than its N-d-methyl or dis-methyl metabolite of morphine. Okay, so if we need to explain about other thing, which is about the rule of function group in the absorption and bioavailability, we can discuss this with example of a testosterone and the methyl testosterone. The addition of a methyl group can hysterically block metabolism of the testosterone and thus increase the duration of action of a specific drug molecule like a testosterone. So if you look with me, the testosterone, which contain here hydrogen, but when we replace hydrogen with a methyl group CH3, this will make the structure as the methyl testosterone. Here what happened? That we will find that the presence of the methyl group make crowding in this area. And when it make crowding, the metabolism through that this OH action on the OH, this will be inactive or will not occurring quickly. So the testosterone less in the duration than methyl testosterone, because methyl testosterone have a metabolic blocker with modification by adding a steric hindrance, a crowding, a more crowding group, which is the methyl here. Okay, so this is about the function group and its role in absorption and bioavailability, which can leading to this increased duration of action, but also in the absorption, it can present as the testosterone, which is that more hydrophilic than the methyl testosterone. So we can found that the administration, that this block oxidation metabolism allow methyl testosterone to be administered orally. Okay, why? Because that additional methyl group at the position of the carbon number 17 position converts the secondary hydroxyl group into a tertiary hydroxyl group. And this is instead of that, this hydroxyl group was secondary in the testosterone. When we adding here CH3, that makes this hydroxyl group as a tertiary. And in the tertiary, it is not able, the tertiary or that the tertiary hydroxyl group or the tertiary alcohol cannot be oxidized. So it will be not able to oxidize at this moment that we block the oxidation metabolism, and this allow the methyl testosterone to be administered orally. Okay. Other example, which is about that acyclovir and the valcyclovir. The acyclovir demonstrate very poor oral absorption alternation of the highlighted hydroxyl group to a valine ester provide a significant increase in the oral absorption. Here, guys, if we look, we will find what? We will find this end with the hydroxyl group here. But here, it instead of the hydroxyl group, it begin to be this group, which is that the highlighted group is begin to be like a valine ester. Okay, and the valine ester, it will make it more oral absorption. More oral absorption. Why? Because the valine will help, as an ester, will help to make the compound is more and more absorbable. Okay, but in case of acyclovir, which contain the hydroxyl group at the end, it is poor to be absorbed like this. In case of the acetylcholine and the beta-nicole, the methyl group in beta-nicole offers several advantages for beta-nicole over acetylcholine, as acetylcholine non-selectively interact with both muscarinic and nicotinic receptor. It's rapidly metabolized by acetylcholinesterase and is not already active. At the same moment that the additional methyl group in beta-nicole allow it to selectively interact with muscarinic receptor and prevent its degradation by acetylcholinesterase, thus allowing it to be administered as an oral tablet. So that is selectivity in that the action muscarinic nicotinic will be non-selective like acetylcholine, but presence of the methyl group make it like a beta-nicole is more selective on muscarinic, not nicotinic. At the same moment that the presence of methyl group in beta-nicole allow more than allowing selectivity into the muscarinic receptor. Also, it can prevent its degradation by cholinesterase, inhibit the acetylcholinesterase enzyme, and it will be easy to administer as an oral tablet. Other importance of the function group in the selectivity and the drug metabolism. We just explained about the selectivity in muscarinic nicotinic. For acetylcholine, it can act on muscarinic and nicotinic, but beta-nicole with the methyl group, additional methyl group, it can make it more selective for muscarinic. And also, in case of terbutaline, as you look, guys, we have a group D and group E. The group D, which is about them, the group D, which is about hydroxyl group, and the group E, which is about the tertiary butene. We can find that the group D moved one carbon away from the other hydroxyl in order to decrease the metabolism of our molecule. It also helped to provide selective beta-2 action. Here, guys, if we know that this is terbutaline is a derivative of the norepinephrine and epinephrine. It's mainly epinephrine. Okay, so we can find what? We can find that CH3, for example, here. Okay, and that's the catecholamine, which is that the epinephrine. Okay, so in the epinephrine, we can find that methyl group present on the amine, and there's here catechol. That's the catechol. Okay, at which that the comet act here. Comet enzymes that metabolize catecholamine, called catechol or methyl transferase, act when there is a catechol structure. But here, to not make or not allow the comet to act on this structure, so the hydroxyl is far from each other by one carbon. So it is now not a catechol. So comet can't work on this terbutaline structure. So this is increasing duration of action. Number one. Number two, also that selectivity to beta-2 action, that we found that the hydroxyl far from the other hydroxyl in the catechol bar. In the group E, which is the presence of terbutyl in the terbutaline, it provides more selectivity for the receptor of the pulmonary system, which is that action on the beta-2 receptor more than acting on the beta-1 or the alpha also. So there is more selectivity in the receptor that present in the pulmonary system, which is the beta-2. So it decreases the side effect or the unwanted adverse event or side effect. Other important that we will discuss in the future, in the next lecture, is about the chemical properties of functional groups. Okay, by this we finish about this lecture. Thank you.